Year 13, Chapter 10, Integration, Lesson 3, Integrating Trigonometric Functions. So we're going to start off by reminding ourselves that integration can be considered the reverse of the differentiation process. And we know that if we differentiate sine x, we get cos x. If we differentiate cos x, we get negative sine x, and if we differentiate tan x, then we get sec squared x. So from here, we can then think of these processes in reverse, because what this tells us is that the integral of cos x is sine x. The integral of sine x is negative cos x, and then the integral of sec squared x is tan x. We will later on learn how to actually integrate tan x as well. Now this works because if we start with sine x and we differentiate it, we get to cos x, which means that if we integrate, taking integration as the reverse of differentiation, we go back to sine x, so the integral of cos x is sine x. If we differentiate cos x with respect to x, we get negative sine x. Now this means that if we integrate negative sine x, we get cos x as an answer, but it's much easier for us to write it out as the integral of sine x, so we simply move the negative to the other side. And of course, if we differentiate tan x, we get sec squared x, which means integrating sec squared x takes us to tan x. And as I've said, we will learn how to integrate tan x itself a little bit later on. So make sure that you know and have learnt these three results here. So we're going to have a look at how we can use integration by substitution to perform various trigonometric integrals. Let's look at this example here. Can you see it's a composite function? We have 2x plus 3 and then we have the sine of this. So here's my inner function, u, and I'm going to differentiate it. I'm going to use the long format of integration by substitution, and then we will do our faux rearrangement, so dx equals du over 2. Remember, we write that in the quotation marks because it's not really a real piece of maths, it's just a very convenient shortcut. So this is then the integral of sine u, but instead of dx, we can replace that with du over 2. I'm going to pull out the half, so we've got a half, the integral of sine u du, so that is a half, and then we now need to remember how to integrate sine, and we know that the integral of sine is negative cos, and of course don't forget your plus c at the end, so we get negative a half cos, and then of course we have to replace u with what it is in terms of x, so 2x plus 3, and then there's simply a plus c at the end. So here is the original integral, and here is the final answer. Now, can you see how this could be done in one single step without necessarily having to use the full integration by substitution process? We know that sine integrates to negative cosine. So in our answer, we have negative cos 2x plus 3. So sine integrates to negative cos, but then of course there is a factor of a half here, and where does that come from? Well, we're dividing by the derivative of this inner function here. So let's take a look at another example. It's another composite function, cos of 4x minus 1. And I'm going to attempt to integrate it by inspection, which is the name that we give to this very quick method of integration by substitution. So by inspection, I look at the fact that this is a cosine function, and we know that cosine functions integrate to create sine functions. So cos of 4x minus 1 will integrate to give me sine of 4x minus 1, but I need to make sure I divide by the derivative of this inner function that I've highlighted in green, and the derivative of the inner function is 4, so I need a factor of a quarter here, and then plus c. Now, let's double check that by using the full integration by substitution technique. So I need to set u equal to 4x minus 1. Differentiate, du by dx is 4. And then our faux rearrangement, we have everything we need. So we're integrating cos 4x minus 1 with respect to x. So this then becomes the integral of cos u. And instead of dx, we have this. So if I pull a quarter out of the integral, we then just simply have a quarter sine u plus c, cos integrates to sine, and so we get a quarter sine 4x minus 1 plus c, remembering that I need to replace u with what it is in terms of x. So we get exactly the same answer by inspection as we do by doing the full integration by substitution method. So let's look at one last example. Now, there is a factor of 2 here, which will just be a multiplicative factor in the answer. I'm going to do this integral by inspection. So I'm simply going to look at the fact that my inner function is a linear function. That is very important. It has to be linear, otherwise we can't really use this inspection method. I can see that this is a sec squared function, and I know that sec squared integrates to give me tan x. So I can say that I get tan of 5x plus 1. But then I need to make sure I divide by the derivative of this inner function, which is 5, so I get 2/5 tan 5x plus 1 plus c. So let's see if we can generalise this. Now, before we do this, in each example, look at the inner function. In every case, it's of a linear format. This will only work, this inspection method will only work if the inner function is linear. So, let's start with the first one. It's a sine function, so it will integrate to negative cos of ax plus b. But of course, we need to make sure that we divide by the derivative of this inner function, so we want 1 over a here. The next one is a cosine function, and we know that integrates to a sine function, so it will integrate to sine of ax plus b. But we need to divide by the derivative of this inner function, which of course is just a, so we end up with 1 over a here, and of course plus a constant at the end. The next one is a sec squared function. We know the integral of sec squared is tan, so we'll get tan of ax plus b, and we need to make sure we have a factor of 1 over a here, and plus c at the end. So we can integrate any of these simple trigonometric functions when the inner function is linear using inspection, or we can use the full integration by substitution process. So let's now have a look at an example that is a definite integral, i.e. one that involves limits. Now, one key point that we have to make very clear at the start is if we're dealing with a trigonometric function and we're either differentiating or integrating, we have to work in radians, otherwise our answers will be incorrect. So always take a moment to stop, check the mode of your calculator, check that you are working in radians whenever you integrate or differentiate a trigonometric function. Now, I'm going to do this by inspection rather than using integration by substitution. If I wanted to use the full integration by substitution process, I would set u equal to a half x, but it's such a simple integral that I'm going to do this by inspection, which means I can work entirely in terms of x and I don't need to change the limits. So we know that cos integrates to give us sine, so we'll get sine of a half x. But of course, we need to divide by the derivative of this inner function. What is the derivative of a half x? It's a half. Dividing by a half is the same as multiplying by 2. Now, as I said, because I didn't change the variable, the limits stay in terms of x. So next, we simply substitute in these limits. So that gives me 2 sine pi by 2. Take away 2 sine 0, pi by 2, when we take the sine of that, that's equal to 1. So the final answer to this integral is 2. Now you may wish to try this using the full integration by substitution method, in which case you must change the limits to new values in terms of u. So we're going to finish off by looking at 3 examples involving integration by substitution. And the integrals are slightly more complex than the simple integrals involving the linear inner functions that we've just been working with. So we're going to use the full integration by substitution method. Now, you will come to recognise the format of these sorts of integrals, where one part of the integral differentiates to another part of the integral, and so you get a very neat cancellation. Now, u equals cos x. If I differentiate this, du by dx is negative sine x, which is another part of the integral. Let's do the faux rearrangement. So dx is equal to du, or negative du over sine x. And you can instantly start to see there's a sine x in the denominator here, a sine x up here. There's going to be some sort of cancellation. So recognising when one part of your integral differentiates to the other part of your integral is a very, very important skill in spotting when you can do an integral by substitution. So this is how I'm going to do it. I'm going to leave sine x as it is, just for the moment. I'm going to replace cos cubed x, and remember, cos cubed x is the same as cos x all cubed, so in this case, that's u cubed. So I get u cubed, and then in place of dx, I need to write negative du over sine x. Now, look at the neat cancellation. As we predicted, that is going to disappear. Sine x is going to disappear, so we then pull out the negative sign for simplicity, and we have negative the integral of u cubed du, an indefinite integral, very easy integral now to do. So this then becomes negative u to the 4 over 4 plus a constant, and then I'm simply going to replace u with what it is in terms of x, so that's cos x all to the power of 4, but of course a much neater way of writing that is to use the notation when we write cos to the power 4x. So here's another example. Can you spot which part of this differentiates to another part? Because that will give you a good hint as to what u is. Did you guess correctly? U is x squared, which we know differentiates to 2x, which is another part of the integral. Let's do the rearrangement, the pretend rearrangement, and then let's start substituting in. So I always leave this x here. We know it will cancel out, but we may as well leave it for the moment. And then we have sine of x squared, which now becomes sine of u. And then in place of dx, of course, I want to write du over 2x. So, as predicted, x cancels. We can pull the factor of a half out of the integral, so we have a very simple trigonometric integral. And we know sine integrates to give us negative cos. So here's our answer in terms of u. And then the only thing we have to do is replace u with what it is in terms of x. So we have negative a half cos x squared plus c. Now, notice the way that we've written out sine of x squared and cos of x squared, because this is very specifically cos of x squared, and this is different to cos squared x, which of course means cos of x all squared. Okay, so please make sure you understand the difference between cos of x squared and cos x all squared, or cos squared x. They are different concepts. Let's look at one last example. Now, notice that it's a definite integral. You can see the limits here. We must work in radians because trigonometry is involved. If you are integrating or differentiating anything that involves a trigonometric function at any stage, you need to make sure you are working in radians, otherwise your answer will be incorrect. Now, look at the inner function here. U equals 2 minus x squared, and of course, when you differentiate that, we'll get negative 2x. So you can start to see how this will rearrange and how a cancellation will occur. Now, we also need to make sure we change the limits. They're currently in terms of x, and we need to change them so they're in terms of u. So x equals 0. I can work out what u is by substituting into this result here. If x equals 0, u is equal to 2. And if x is equal to 1, u is equal to 1. So I have my new limits. So my integral becomes the integral of, now my limits, my lower limit is now 2 and my upper limit is now 1, which is a bit weird to have a larger lower limit than an upper limit, but it's fine. We can still carry out the integral as we have been. So we'll just continue. We have this x here, which we know will cancel in a moment, but I'll leave it there for just now. We then have cos of u, and then in place of dx, I have du over negative 2x. So the first thing that I'm going to do is to cancel x and x, and then I'm just going to rewrite my integral as negative a half. So I pulled that factor of 2 in the denominator out, and then we'll just write down the main body of the integral. Now, we can do the integral as it stands. It is perfectly acceptable, even though the lower limit is larger, to carry out the integral as it is. However, there is also a nice rule that we can use here, which is the integral of a function between two limits, let's call them a and b. If we reverse the order of those limits, so we get b and a the other way around, we get the negative of the original integral. So how does this help us? Well, it means that if I switch around the limits, so I have 2 here and 1, as long as I negate the integral overall, the answer will still be the same. And of course, if I negate negative a half, it just becomes positive a half. So by doing this, I actually make the integral much, much simpler. So this then becomes a half sine u between 1 and 2. And because I changed the limits, I don't have to put the integral back in terms of x. I can simply substitute in my limits and work out the answer. So this comes to an answer of 0.03391, 0.0339 to 3 significant figures. You will only get the correct answer if you're working in radians. If you work in degrees, you will not find that you get the correct answer. Now, really important that we're all aware of this result here, which is extremely useful. So make sure that you know it. You can change the sign of an integral if you swap around the limits, or if you swap around the limits, you can change the sign of the integral and still get the same result at the end. So we'll finish this lesson by looking at how we can use trigonometric identities to help us with integration. So we're moving away slightly from the integration by substitution processes. Now, we're going to integrate tan squared 3x. And you might be thinking, well, how can we integrate tan squared when we don't know how to integrate tan? But you may recall there is an identity which tells us that 1 plus tan squared x is equivalent to sec squared x, which can be rearranged, so tan squared x is equivalent to sec squared x minus 1. Now, we're dealing with tan squared 3x, so if I adjust this to tan squared 3x in the identity, that is then equivalent to sec squared 3x minus 1. I'm simply replacing this angle here and replacing it with this angle here. It will work. We know the identities are true for any value of x, which means they'll be true for 3x. So I can now rewrite my integral as the integral of sec squared 3x minus 1. Now, can you see how this helps us? Well, sec integrates to tan. So by inspection, we can say we get tan of 3x, but of course we need to divide by the derivative of the inner function, so we need to divide by 3. So 1/3 tan 3x. Of course, we then have this part here, minus 1, which simply integrates to minus x. And then don't forget plus c at the end. So, what about sine squared x dx? Now, there is a temptation to just say, well, isn't it just sine cubed 4x over 3, trying to raise the power by 1 and divide by the new power, but that only works with a linear function, and sine is not a linear function, so we can't just do that. We have to be a bit more careful in how we go about this. Now, there are 3 identities that involve sine squared x. There's the identity cos squared x plus sine squared x is equivalent to 1. There's the identity cos 2x is equivalent to cos squared x minus sine squared x. And then there's the other identity for cos 2x, which is equivalent to 1 minus 2 sine squared x. Now, one of these identities will help us, the other 2 will not. Can you work out which one is the useful one? Yes, it's the third one. This one won't help us because it will introduce cos squared into the integral, and we don't know how to integrate cos squared at the moment. This one won't help us because it too will introduce cos squared into the mix. It's this one that will be useful to us, and I'm going to rearrange it. So 2 sine squared x is equivalent to 1 minus cos 2x, and then divide by 2, sine squared x is equivalent to a half minus a half cos 2x. Or, if you prefer, a half bracket 1 minus cos 2x. It doesn't really make any difference. So now I can replace sine squared x with this or with this. And I'm going to choose the second one. So that's a half 1 minus cos 2x. And I can pull that factor of a half in front. So I've simply now got to integrate 1 minus cos 2x, and this is really easy to do. Let's leave the factor of a half here, and then the rest of this becomes, well, 1 integrates to give me x, and then cos 2x integrates to give me, well, cos integrates to sine, but then we need to divide by the derivative of this inner function here, which is 2, so that gives me a factor of a half, and then don't forget plus c. Now we can expand, just for clarity, and this gives us our final answer. And this is really important. If you're asked to integrate sine squared x, you need to remember that it's this identity that will help you do it. So can we do something similar if we have an identity that involves cos squared x? Yes, we can. So there are, again, multiple identities that involve cos squared, but we want to use an identity that does not involve sine squared. So that means we need to use the identity cos 2x is equivalent to 2 cos squared x minus 1, as this will allow us to simply replace a cos squared function with a single cos function. Let's rearrange. So this tells me that 2 cos squared x is equivalent to cos 2x plus 1, and then dividing by 2, cos squared x is equivalent to a half of cos 2x plus 1. So here's my rearrangement, and looking up here again, I've got a 4x here. So I have cos squared 4x. Now, remember, these are double angle formulae, so if x has become 4x, it's being multiplied by 4. Look at the relationship here. This angle here, 2x, is double this angle here, x. So on the right-hand side, I must have cos 8x plus 1. Now, if you're finding that a little bit difficult to see, then go back to this result here and then swap it so that you make sure you have cos squared 4x. So remember, it's a double angle formulae. So you're going to need to have 8x here to get 4x here. And then, of course, you can rearrange that for your cos squared 4x. So work through the algebra really carefully to make sure you understand that. So my integral is now going to become a half cos 8x plus 1 dx. So integrating cos, well, we'll get sine 8x, but we need to divide by the derivative of this inner function, so we'll get a factor of an eighth, and then this part here will simply give us an x, and let's not forget plus c at the end, so we end up with 1/16 sine 8x plus a half x plus c.